Yes, we are on live. Yes, Mr. Rothari, over to you.
Thank you, sir. Good afternoon, everybody. Today is 7th December, and I would like to quote the words of Novel Yuval Harari, the famous historian from the Oxford University. When you read the *Sapiens* books, he started his book from the line that the first it was the matter and energy which came into the existence, that is physics, and after that chemistry followed, and after that the biology. Today, we are having with us Dr. Bikram Phookun from Delhi University, St. Stephen's College, who would like to enlighten us in physics, how physics can create virtually all the areas. If you remember, audience, Elon Musk, who is the second richest person right now and the owner of SpaceX company, he is also from the physics background, and he says that I am here because of the physics. And you can look into any area. Now, without making taking more time, I would like to pass the mic to Dr. Ashish Raturi from Dolphin Institute of Biomedical and Natural Sciences, who is hosting college of this prestigious talk of this intellectual speaker. Thank you, sir. Over to you.
Thank you, Rohit. And I welcome to you all in this very important event. And the title of the talk, as Rohit said, the speaker of this event is Professor Bikram Phookun. And I have a very little knowledge about the Professor Bikram Phookun because I knew him from last couple of weeks when I read the first his article on which is concerned to related to how the physics prepares students for virtually all professions. So it was very interesting for me. I am very impressed after reading that particular article of Dr. Phookun. Then I have request to him now if he has time, then he can deliver the same topic or same concerned thoughts among our students. So he is here, and I'm sure that Dr. Bikram Phookun is a professor of the Department of Physics, St. Stephen's College, Delhi, where he has been teaching since 1996. He holds a PhD in astronomy from University of Maryland at College Park, USA, and BSc and MSc in physics from St. Stephen's College, Delhi University. He set up the physics program at Ashoka University, where he served as a professor of physics from 2017 to 2019. Presently, he is working as a professor at Department of Physics at St. Stephen's College. And as much I know about the Professor Bikram Phookun, and he is also a recipient of the INSA Teacher Award. And Dr. Phookun belongs to that category of intellectuals in this country who has a gumption to question about the status quo, and who is surely able to shift us from our comfort position to thinking about the new dimensions of physics, especially for the students. Definitely, this talk will be enhance your interest towards the physics. So, without any further ado, I would like to invite Professor Bikram Phookun. Please, sir. Now, mic is over to you.
Thank you very much, Ashish. Will I see the audience? Who is in the audience? I can see only you.
It's a live, so everything is on a live mode. We cannot at this time see the audience.
Oh, okay. All right, so you can't show me the audience, but can you give me some idea of the audience? Who are the
one sir before
who are?
Yes, I will. The audience are the undergraduate students, postgraduate students from the different stream of the sciences. And before giving the mic to Professor Bikram Phookun, I would like to request audience, they can make a questions. If you have their queries, they can raise your questions on the chat box. And definitely, I would like to request to Professor Bikram Phookun to answer after his talk. Okay, thank you, sir.
All right, so let me begin right now. It's 12:05. I think I'll take about 45 minutes. And so that should leave about 10-15 minutes at the end for questions. I hope that's okay. I actually didn't realize that the consequences of writing an article for Facebook would be to give a talk somewhere. And I was a little taken aback when Dr. Raturi invited me to give this talk, but I thought, why not? Let's give it a shot. I'm also not used to talking to an audience of people from the life sciences and medical sciences, because my audiences are generally from physics. But I'm going to give it a shot, and I'm going to say things that I hope are sufficiently general that they will make sense to you. And as he pointed out, this talk is based on, but not exactly identical to, an article that I wrote on Facebook and that I invite you to read later. Okay. I hope that Dr. Acharya will provide the link on to all of you, and you can read that article on Facebook. I've actually written a lot of articles on Facebook about teaching, and you're welcome to read those other articles too. Okay, let me begin with a caveat. I mean, let me just say that it is not true that physics prepares you for all professions. I mean, there's nothing obviously that can prepare you for everything. It's a bit of an exaggeration, but it is a reasonably honorable exaggeration in the sense that physics prepares you better than I think most other subjects that are taught at the undergraduate level. Okay. So in that sense, physics prepares you more widely than I would say, most of the other sciences for further career in any of those sciences. So for example, a significant number of my students after doing physics turn to biology. And biology is going through a kind of revolution in which they're welcoming people from all kinds of backgrounds, people from mathematics, engineering, physics, and so on, because new methods are being used to understand and manipulate the subject. So it is in that light that you should understand this title. You shouldn't take it literally. Now, what is it? I want to tell you what it is about physics that, in my opinion, makes it a science of such broad applicability. I think the first thing is that it picks up on something that is very fundamental to all human beings, and it then sort of refines that and applies it in a very kind of organized and methodical fashion, which is the idea of hypothesis making. Now, if you think about it, hypothesis making is sort of what you do all the time. Okay? In fact, neuroscientists have shown that hypothesis making is the way one understands the world. Even a child, even a baby is constantly making hypotheses about the world that he or she perceives. And it is by matching the hypotheses to the reality observed through the senses that reality is understood and the hypotheses improved. Okay, so it's a kind of dual process where you at the same time understand something and on the other hand improve the tools through which you understand them. Okay, and if you think about it, that's sort of what we do even as adults between adults. So for example, if you're having a conversation or an argument with someone and you say something and the other person responds, it is very seldom true that you or the other person reaches the point immediately. You say something, the other person improves on what you say, and then you say something else, and slowly you make your way towards a truth or something that both of you can understand and accept. Okay? And this is a very, very common process. So in some sense, you're making a hypothesis, and the other person is refuting the hypothesis or improving it, and this process continues until you're both satisfied. Okay? And this is sort of what we do in physics, except that in physics, this is refined to a very, very great extent. Okay, the process of hypothesis making is very, very precise. It's usually a mathematical hypothesis. And the extent to which you can match your hypothesis with the external world is also extraordinarily precise. So for example, if you drop a ball, to most human beings, the ball is falling. But to a physicist, it's not just a question of the ball's falling. The ball is falling at a certain velocity, and furthermore, its velocity is increasing in a particular way. Okay? So you can make predictions about the exact motion of the ball as it falls, or as it describes any other kind of trajectory, as a planet goes around the sun, as electromagnetic waves propagate through a medium, and so on. And these predictions can be then matched precisely with observations. So the precision with which hypotheses are made and the precision with which hypotheses are matched with observations is something that is really the heart of physics. This is what physicists do. Physicists make hypotheses and they match hypotheses with observations, which means that They have to develop tools to make extraordinarily good observations, and they also have to develop the tools to make extraordinarily good observations, and finally they have to have a way of connecting those two. Okay? And in some sense, this is what all of science is about. This is what you do irrespective of what you do in science. And it's not just science, it's sort of something that you do in various disciplines, but more so in science than anything else. So for example, if you're doing biology, you make a hypothesis, okay, about something. So Darwin's theory was originally a hypothesis. He makes a hypothesis, and then he goes out and finds evidence that corroborates his hypothesis. And this is the fundamental act of science. Okay. Sometimes people imagine that science occurs through these sudden leaps of the imagination. And it is true that on the outside, you sometimes get what looks like a leap of the imagination. But usually behind that leap of the imagination, there is a process. And this process is a process of iterative hypothesis making and confirmation. Okay. And this thing is really the heart of physics. And once you get that, you sort of understand how to go about doing physics, and thus understand how to go about doing almost any other kind of science, which is why I think physics teaches us something that is central to all of science, and in fact, all of understanding in general. And so this is a very, very important thing. And I want to get this across because the way physics is taught in school is usually as solutions to problems. There's a problem, and then there's a solution to the problem. So the way people prepare, for example, for the IIT entrance exam is to learn hundreds of problems and how to solve these hundreds of problems. But in my opinion, that is, completely the wrong approach to understanding anything. That is not the way to do things. As I point out to my students, I mean, if there's no point learning problem A, problem B, problem C, problem D, problem all the way to Z, when you could learn some problem, an overall problem that explains all of these other problems. The idea is to understand it at a sufficiently deep level that you can make a hypothesis that explains things, rather than trying to map solutions to problems. Okay, and unfortunately, mapping solutions to problems is the way physics is learned. So people get the wrong impression about physics when they're in school, and often when they come to college and start learning physics the correct way, it's a bit of a shock for them. Okay, I mean, for example, most of my students go through a phase of shock when they come to first year, and they're taught how to think rather than just to find solutions to problems. Okay, and but this is the central lesson of physics, that you have to learn how to make hypotheses, you have to learn how to confirm hypotheses, and you have to go, you have to learn how to sort of stretch your hypotheses, how to find the limits of your hypothesis, how to get the most out of your observations, how to make new observations to confirm new things that have emerged from your hypothesis, and so on. So it's a very complex and intricate process that in some form appears in all of the sciences. Okay? That's the first point I want to make. And this point is, I think, the central point. If you get this point, you've got most of what I want to say. The other points are elaborations on this point. Another point that I want to make is the difference between description and understanding that is also very central to physics. Often I find, for example, in the classroom, when I ask a student a question, they give me an answer that is essentially a paraphrase of what I've said, but in different words. So in some sense, what they've done is they've described what I've said. Whereas what I'm looking for is something that is an explanation of what I've said. Now, what is the difference between a description and an explanation? This is, again, something very, very important to understand, because in physics, the idea that an explanation has several levels is also very central. And this is something that is not very clear necessarily in all the sciences. It's very, very clear in physics. And it just struck me this morning that it's also very clear in medicine. So I'm going to use, I'm going to first give you an example from physics, and then I'm going to go on to this idea in medicine and give you a way of understanding what I mean. All of you, I'm sure, have heard of Kepler's laws. Kepler's laws are the laws of planetary motion. Okay? I'm sure that if you went to school, you did science, you're at least familiar with Kepler's law. What do Kepler's laws say? Kepler's laws say that each planet goes around the sun in an ellipse, with the sun at one focus. And there are two other laws that covers equal areas in equal times, and there's a relationship between the time period and the semi-major axis. Okay, t squared is proportional to a cubed, I think, something like that. Okay. Now, suppose I ask you why a planet goes in an ellipse around the sun. And you say, it's because of Kepler's first law. Okay. my immediate response would be, you haven't provided me an answer to the question. That is not the answer to the question. Okay? Because what Kepler's laws did was simply to describe the observations of the motions of planets that were available at the time of Kepler. There was this famous observer by the name of Tycho Brahe, who made a Danish astronomer who made observations of the motions of planets. And Kepler put all these observations together and found patterns in the motions of planets. Now, this is a very, very important process in the process of science, in the process of making a hypothesis, or in the process of understanding. But it's also very, very important to understand that what Kepler was doing was not providing an explanation. He was not providing an explanation. He was providing a description of what was happening. He was providing a description of what was happening. So if you tell me that a planet goes in an ellipse around the sun because Kepler's first law says so, you haven't provided me an explanation. You've simply given me a description of what is happening. So what is the explanation? The explanation comes with Newton, because what Newton does is provide a theory of all motion without reference to the planets or without reference to anything. He just says objects move in this particular way. Now, if objects move in this particular way, and planets and the sun are also objects, then the laws that we figure out for the motion of objects must also apply to the planets and the sun. So what you do is you take these general laws, which are in some sense explanations of all motion, okay, and you apply them to the motion of the planets, and you find that Kepler's laws, lo and behold, are true. Okay, so it's amazing. You find that Kepler's laws hold as a result of certain laws of motion which apply not only to the planets but to all motion. Okay, so Newton's laws are a far deeper level of hypothesis making than, so Kepler came up with a description, and then Newton came up with an explanation for the patterns found in that description. And this is a central feature of all hypothesis making in physics, and it's very, very important. It's very important, and I want to give you an example from. I want to give you first an example from medicine, and then I want to give you another example from physics where you will understand this better. So, for example, if you're a doctor trying to diagnose a disease that a person has, okay. Now, there are various different levels at which you can do the diagnosis. Okay, you can have a fever because you've got the coronavirus, for example, the most fashionable disease at the moment, or you got something else. You got you got a cold or something, and you could also have a fever because there is a problem with a much larger problem with your body. Okay, for example, there could be a cancer somewhere in your body, or you could have a fever because there is something wrong with one of your genes, which has expressed itself as a problem in the body, which has further expressed itself as a fever. Okay. So my point is that when the doctor is trying to understand why you have a fever, he or she must first understand whether it is a problem at the level of a fever attacking an otherwise healthy body, or a fever attacking a body that suffers from a deeper condition, or a fever attacking a body that suffers from a deeper condition because something even deeper than that condition, the genetic structure itself, is at fault. Okay. So there are different levels at which the doctor can understand why that disease has occurred. Okay. The process of diagnosis, therefore, automatically allows different levels of understanding. In exactly the same way, when you understand a phenomenon in physics, you automatically tend to understand the phenomenon in terms of layers, an outer layer, a middle layer, a bottom layer, and so on. And this is very, very important, because then you know that you can't lightly change the bottom layers. So if you go to a doctor with a fever, the first hypothesis he or she will make about your disease is not that there's anything wrong with your genes. That hypothesis will not even occur to him. Okay. Nor will it occur to him that you've got some extremely serious disease. He'll probably first look at the likely causes. Okay. And once those are eliminated, then you modify your hypothesis, go deeper. If that doesn't work, you modify your hypothesis, you go even deeper. Okay? And this process is a very, very important process, and it is a more refined version of hypothesis making. Okay? This also appears in other branches of science. A very famous example from physics. Okay? It has to do with the name of Einstein. Some of you may have heard of this example. Some of you may not have, but it's a wonderful example of how hypothesis making works in physics. Now, as I just told you, Kepler came up with a description of the motion of the planets. Newton came up with an explanation of Kepler's laws, which is a description of the motion of the planets. And the motions of the major planets were known until most of the major planets that were known until the early part of the 20th century had already been described. Okay? And they had gone one step further and also been able to describe how when you have not one planet, but more than one planet orbiting the sun, their motion interferes with each other in such a way that you need to make small modifications to your understanding of the orbit of one planet. Okay, one particular modification is a very important one. So, for example, if you think of a motion, a single planet going around the sun, it has the shape of an ellipse. An ellipse is like an anda. It's an egg. Okay, it's pointed in one side and flat on the other side. And if you have any other object also in the solar system, then what happens is that the pointed part of that ellipse tends to keep changing its direction. Okay, it keeps changing its direction, and this is a process called precessing. It's called precession of the orbit. Okay, it's a very small effect, but it is an effect that with modern observations one can detect, and with modern theoretical tools one can completely explain. Okay. So it turned out that the planet Uranus was showing certain motions that could not be explained on the basis of the gravitational field of the sun or the gravitational effects of the other planets that were known at that time. And so a couple of scientists came up with the hypothesis that there existed one more planet. Okay. And they even worked out where that planet needed to be. Okay. And lo and behold, when observations were done, another planet was found there. Okay. And this planet is Neptune. That planet had not been detected until that moment, but because of the belief that the theory worked out so far was true, and once it was applied to the motion of Uranus, you could deduce that another planet must exist. And this is a wonderful example of how you can discover new things simply from belief in your hypothesis. Now, let's go one step further. It turned out that there was one more planet whose motion was not entirely explained, and that was Mercury. The Mercury is a planet which is closest to the sun, and it was discovered that the amount by which its orbit precessed, you don't have to understand all the words that I'm saying. All I'm saying is the amount by which its orbit deviated from what it would have been if all the factors known until that moment had been taken into account was not complete. Okay, there was a certain kind of margin of error still left. And so naturally, having discovered Neptune through a margin of error, scientists came up with the hypothesis that there must exist one more planet there. In fact, so strong was the belief in certain minds that another planet was there that they even named it. They named it the planet Vulcan. But no matter how hard they looked, they couldn't find Vulcan. And then Einstein came along and he looked at these observations and he realized, that it could be something deeper than that. Maybe the theory of gravity itself needed to be modified. And he came up with a new theory of gravity, which is called the general theory of relativity, which predicts everything that Newton's laws do and more. And in particular, it was able to predict the additional precession, the additional motion of the orbit of Mercury. So completely that when Einstein discovered this, apparently he couldn't sleep for 3 nights. It was such an extraordinary moment in the history of science. So what I'm trying to get at is that this multi-layered structure of the hypothesis is a very important thing, not just in physics, but in other areas of science as well. I just pointed out, I gave you an example from medicine. I'm sure you could find examples in biology and so on. Okay. Similarly, for example, if you're applying the theory of evolution, there would be the deepest level, and then there would be other levels, and you would modify them. If you would modify your theory from the most superficial level downward. You don't immediately modify the deepest level. Okay? And this is a very, very important lesson, which is very difficult to learn. It's not something that you can learn simply by arguing with someone. The kind of normal hypothesis making that we do does not teach you this level of sophistication in hypothesis making. But physics does, because this is what physics is about. Okay? Everybody who learns physics has to learn this. All undergraduate students of physics have to learn this. They have to learn how to make hypotheses, how to apply hypotheses, how to apply them in layers. Okay? So it's so central to physics that if you're trained in physics, you automatically learn this very, very important skill. Okay? All right, that brings me to that's the second point. Okay. A third point, and this is something that is just not taught in school at all. And I just wish that this were taught in all schools, because this is something that does not require any sophistication. It just requires a change of mindset. Now, just go back to your school days and imagine what happens when your professor or teacher asks you to solve a problem. They describe the problem and they tell you what the force diagram is and immediately begin solving the problem and you find the answer. And then you go through the same problem 1 million times so that you have it by heart, and when the exam comes, you know exactly how to write down the solution. Like I said, this is completely the wrong approach to learning anything. Okay? This is just upside down, okay? Because you're essentially focusing on the solution. As one of my students famously said to me once, until I came to St. Stephen's College, I never saw a problem, the solution to which I didn't already know. Because in school, what you're taught is to already know the solution when you see the problem, and then somehow figure out a way to that solution. That's not the point. The point is to learn how to get to that solution. And to learn how to get to a solution, there is a whole process. And the most important word in this process is notice. This is one of my favorite words in the class. That whenever I write an equation down on the board, or I draw a diagram of a physical situation, or I point to observations, I almost never begin working things out immediately. So what I will do is I'll ask my students to notice various features of the problem at hand. And let me give you an example from something that I read about. It's something that happened in a school somewhere in the United States. The teacher was trying to get the students to understand the motion of a pendulum. Okay? And this teacher was not a science teacher, I think. Or maybe she had no science background. She was a teacher. She was teaching science. At that level, anybody can teach science. So what would happen normally in the classroom? The teacher would tell you there exists something called a simple pendulum. Sorry, I went offline. Where was?
Yes, sir.
Where was I?
Now you are live.
Where was I when I stopped? When you last heard me? Was I
just like a simple. You are discussing.
Simple.
You are discussing some about some simple.
Yeah. So this teacher went into this classroom which was full of 10-year-olds, and she didn't say a pendulum is an object with a bob at one end and a string of a certain length L with mass m at the end, which exists in the Earth's gravitational field, which has acceleration due to gravity g, and t is equal to 2 pi root L over g, which is essentially the way it is taught in millions of schools all over the world. She didn't say anything of that kind. She just took the pendulum and she let the bob oscillate. Didn't say anything. Then she said, "What do you see?" Now, the 10-year-olds have no idea about the motion of a pendulum. They have never in their life seen a pendulum. Maybe they've seen some grandfather clocks. When we were children, we used to see grandfather clocks. But nowadays, young people don't even see grandfather clocks. So chances are they don't see pendulums very often. They saw something oscillating. And she said, "Do you notice?" So then she increased the length of the pendulum and she oscillated it again. "And do you notice anything?" So some people pointed out, "Hey, yeah, when you increase the length, the time period increases. It takes longer to oscillate." So then she said, "What do you think the time period of the pendulum depends on?" And immediately, the children got very excited and they started making hypotheses. So they said they realized immediately that it must depend on the length. Okay? Because when you increase the length, the period increases. But if you think about it, the way you're taught about the pendulum, you're always told that it doesn't depend on the mass. And you're told this as if it was some God-given gospel. But if you think about it like a common person, a person on the street, would it ever occur to you that the period of the pendulum cannot depend on the mass? It simply cannot occur to a human being. Okay? It is a very deep truth that is not obvious to anyone. Okay? So what do? The children obviously made the hypothesis. Can you hear me? I'm not sure whether you can hear me because your image is frozen. Can you hear me, Ashish?
Yes, sir. We can hear. Yes, sir. We can hear you.
Made the hypothesis that it depends on the pendulum. It depends on the length of the pendulum, and it depends on the mass. Then she made the oscillations bigger, and she asked if the time period depends on the amplitude of the oscillations. And sure enough, the children must have said, yeah, sure, it depends on the amplitude. Because if you think about it like a common person, it seems completely obvious that the bigger the oscillation, the more time it should take. I mean, isn't it the most obvious thing in the world? But the way the theory of the pendulum is taught, you're told right at the beginning that it doesn't depend on the amplitude of oscillation. It doesn't depend on the mass. But these are both very difficult to arrive at. These are not obvious at all. Okay? It is through a process of analysis. So the best thing is not to tell people the whole story at the beginning, but to allow them to discover the story. And unfortunately, we never give our students the chance to discover the story. We tell them the story in advance. We tell them the entire Mahabharata in advance of Kurukshetra and who won, and then we say, now learn the story by heart and tell me tomorrow. That's not the point. The point is to learn how to tell a story. Okay? So the most important thing is to teach people how to look at things very, very carefully. How to remember things in such a way that when they think about them, thoughts occur to them. They get ideas. When they talk about it with someone else, they get more ideas. Okay? When they dream about them, they get ideas. You've all heard about how the benzene ring structure was discovered by some guy by the name of Kekule. Okay? He dreamed about some snake going around and connecting to itself, and he came up with the idea that the structure of benzene was a ring. But all of these things are not going to happen unless you allow yourself to dream, allow yourself to think about the problem, unless you notice all kinds of things. Okay, but this training is not part of our education, because what we do is we tell our kids what the solution is to the problem. Okay? And by giving them the solution, we essentially short circuit their brains. Okay? So this, what a good physics course always does. It actually is not part of most physics courses, but a good physics course, but by a good, really sort of careful physics teacher will include a lot of noticing. Notice this, think about it like this. If I look at it from this angle, what does it look like? If I take it to this limit, what does it look like? Okay? And if mistakes are made, not to squash the mistakes, but to point out, yes, I could have made the same mistake. Why could I have made that mistake? Why is it normal to make this mistake? And where can we get from this mistake? So it's a very, very complex process of noticing. I would not go so far as to say that this happens in most physics classes. But in a good physics class, this does happen. Okay? Because how to notice is one of the most important things in all of science, no matter what you're doing, whether you're a doctor or a biologist or a geologist, you've got to notice. Otherwise, you're simply following orders from someone else. If you want to come up with an explanation yourself, you have to notice. Okay? You have to be a little like Sherlock Holmes, the detective, who looks at a case and he notices something that other people don't notice. It is by noticing things that others don't notice that you make discoveries. You don't make discoveries by noticing exactly what is written in a book, because that has already been discovered by someone else. If you want to make discoveries, you have to notice something that no one else has noticed. And how are you going to reach that point if you don't get into the habit of noticing things? Okay? So noticing is very, very important, and it is a very, very important part of good physics teaching. Like I said, good physics teaching. Unfortunately, bad physics teaching is exactly the opposite, where you're not encouraged to notice anything, you're only encouraged to find the solution. Okay? And this is very bad physics teaching, in my opinion, where you're only encouraged to find the solution, because it just completely screws up the way people think about physics. Okay, they get very frustrated if they can't find the solution. Whereas, like I said, I tell my students, suppose the teacher asks you a question and you provide the solution. What has happened in the classroom? You've given the solution, you feel very good about yourself, the teacher looks at you and smiles and congratulates you. So everybody else in the class thinks, oh, that person is so smart. But they don't think. But suppose you make a mistake. You make a mistake, and then the teacher says, okay, maybe you're on this track, maybe you could do that, gives you a hint. Then all the other people around you start thinking at the same time. You start thinking about it, and slowly you make your way to the solution. But this is exactly what happens all the time in science. If you're a research scientist, you make your way to the solution. You don't immediately find the solution. So actually making mistakes and recovering from them is a far more useful thing to do. And this is part of good physics. Okay? And you can only do this if you notice things carefully. And so I strongly encourage people to make noticing a part of teaching physics. Okay? It's certainly a part of the way I teach physics, at least so long as I'm patient. Sometimes I get a little impatient and then I lose track of that. Okay. Another very important thing about physics, and this is something that turns people off, is that it is actually very, very difficult. I've been teaching physics for 24 years, and Ashish has been teaching it for much fewer years. I can tell from the evidence; he's much younger than me. But
yes, sir.
It's an extremely difficult subject. I'm sure he would agree with me. There are almost no physics teachers who would say that physics is an easy subject. Physics is an extremely difficult subject. So what is the great advantage of its being difficult? The great advantage of its being difficult is that in the process of learning a difficult subject, you learn how to work. Okay. If learning something easy doesn't really teach you how to learn, but learning something difficult teaches you how to learn. Okay. So for example, if you want to be a musician or an actor or a dancer, you know in the beginning that it's going to be a long process. Ye nahi ki stage pe chad gaya or you become a great actor. Okay? It's not going to happen. Open your mouth and you're a great singer. It's not going to happen. Just pick up a guitar and you'll be Jimi Hendrix. It's not going to happen. Okay? It's not going to happen, and you all know that it's not going to happen. But unfortunately, the way we teach physics in school is that we tend to give people the impression that sab kuch immediately ho jayega. So people get very frustrated with the fact that physics is difficult. But if you can get over this frustration and accept that physics is difficult, then suddenly it becomes possible to do things because you understood something very, very central to the process of understanding anything that is worth understanding, whether it's in physics, in biology, in medicine, in anything else. It doesn't matter. In history, in philosophy, in literature, that great things cannot be done easily. You cannot do great things easily. You can't just wake up and, there are all these stories about great discoveries. Great discoveries are almost never made by unprepared minds. You need a lot of preparation to make a great discovery spontaneously. Wake up one morning and find the structure of benzene is because he had thought about it very, very hard for a very long time. Okay. Einstein came up with his theory of gravity suddenly, maybe, but it took him a very long struggle before that. Okay. And it happens to all of us. The discoveries may be made suddenly, but the preparation is long. That to get used to this, okay, better get used to it. Jaldi kuch nahi hone wala hai. Okay, nothing is going to happen tomorrow. You wait. You join college. You want to figure out how a black hole works. Wait for 10 years. That means in another 10 years you can figure out, the gravitational field of the black hole and what will happen, what Hawking radiation is, and all of that stuff. Just because you read about Hawking radiation in class 11 doesn't mean you enter St. Stephen's College and day after tomorrow you will figure out what Hawking radiation is. It's not going to happen. Okay? So physics teaches you this. And this thing is a very, very important process because you learn how to learn. And if you have good teachers, you have the right kind of atmosphere, you have good peers, you really learn how to go through this process of learning something. You take the steps. You learn that you've got to take many, many steps towards understanding something. Okay, and this multi-step iterative process is essential to physics. Okay? And like I said, this is, I have a friend who's learning the classical guitar. The classical guitar is not just strumming the guitar, it's kind of learning classical music through guitar. And it's a very difficult process. So he's been learning it for years. And he goes to Calcutta once a year. I mean, this year, obviously, he couldn't because of the pandemic. Or last year, he couldn't, I think. You go to Calcutta for this event where these gurus of the classical guitar come and they hold master classes. A master class is where a real master of some instrument teaches experts. Okay. And one particular expert said to the students there something that I have repeated to my students many, many times. He said, don't just practice. When you practice, do it reflectively. Meaning that look back on what you're doing and try to improve what you're doing so that you're constantly improving your practice. What happens often in something like physics is that you get stuck. You get stuck in a way of doing things and you just don't improve any further. It's like when you learn a language. To improve constantly in learning the language, you have to keep reflecting on where you are deficient and keep filling in those deficiencies. but if you get stuck, that doesn't happen, and that is very, very true in physics. And so if you're in, again, this is not something that happens all the time and naturally in any physics class, but this is something that is part of good physics, okay, where you're taught how to improve your practice of physics and slowly get better at this. Now, I've sort of told you everything I want to tell you about physics, but I mean, there are certain, like I started with a caveat saying that, it doesn't teach you about everything. I should tell you that, physics also sometimes can lead you along the wrong path, because in some sense, when we make models in physics, we tend to make what are called very simple models, which seems like a strange word to describe anything in physics, because I just started out by saying that physics is very, very difficult. It's just that in physics, the difficulty lies in the technique. Often the hypotheses are very simple. Okay? So for example, since most of you are life science students, if you, for example, go to the National Center for Biological Sciences, okay, there's a large number of physicists there. In fact, I got an email from a student of mine today who just did his PhD in physics and has joined the National Center for Biological Sciences. A number of my students are there on the faculty. And what you'll find is that there is a significant difference in the way a physics person approaches a problem in biology and a biology person approaches a problem in biology. And this is something that's quite puzzling to biologists in the beginning. Okay? So a biologist tends to understand the problem in its entire detail, whereas the physicist tends to want to simplify the problem, get rid of as many details as possible so that only the essential details remain. Okay? Of course, the question remains, what are the essential details and whether this is an acceptable process. So sometimes physicists make hypotheses in complicated situations that are actually not tenable. Okay? And this is something that as life science students you will encounter. If you meet physicists, you'll find that sometimes they make hypotheses which to you seem utterly ridiculous. Okay? But you should give them a chance. Because sometimes with very simple hypotheses, physics can explain a lot of things. Okay? So physics often begins with very simple hypotheses, but because of the way it structures the drawing of conclusions from those hypotheses, it can arrive at conclusions that seem utterly surprising and even bewildering. Okay. So for someone in the life sciences, it's very important to accept that the approach of a physicist and the approach of a biologist to a problem in biology may be quite different, even if it's the same problem that they're talking about. Okay. Can you hear me, Ashish? Your image is frozen. Let me just stop
Yes,
for a
sir.
second.
We can hear you, sir. Your voice is very clear.
All right. Yeah, okay. So, so what I want to say, presumably you have a department of physics in your college, and presumably some of you, or maybe all of you, need to do some physics course. I don't know. I don't know, frankly, what the structure of your course is. I'm a physics teacher, so I teach only physics. But Dr. Raturi presumably teaches physics to students who are not majoring in physics, who don't do an honors in physics, because it's just your institute is in.
I think some internet interruptions are there. And Professor Bikram Phookun, oh, now he joined.
I'm coming. Am I back?
Yes, sir. You're back.
Where
now
was
you
I?
are audible.
When you last heard me, what
you
was
are
I
talking
saying?
about? You are talking about the courses which we are offering. You are talking about the courses which we are offering in this institute related to physics.
Okay. So I don't know whether all of you do any kind of physics, but hopefully, well, so my suggestion is that even if you're doing the life sciences, it would be a good idea to learn physics to some extent. But the way physics is usually learned by biology students is as a kind of suffering. Okay? It's like, oh, ye to karna hi hai. Let's pass this exam. But my suggestion to all of you is that, true, you have to pass that exam. Okay, all of us have to pass exams. And as undergraduates, that is one of our major concerns, and it should be. But try to get the message of physics. That is my suggestion to you. Okay, try to understand what the physicist is trying to do, or what physics is trying to do. Okay, and instead of getting frustrated by all these problems that you have to solve in physics. So when I was at Ashoka, I ran a course called Order of Magnitude Physics, which is essentially thinking like a physicist, taking very simple problems and then thinking about them in the way a physicist would. Ashish, can you hear me? Because your image is frozen.
No, sir, you are audible. You are very clear. We can hear you, sir.
Okay,
Just
I'll go
continue.
on. Let me go on. I can't hear you. Anyway, so I mean, ideally, the kind of physics course that people in the life sciences and other sciences should be taught is not a standard physics course. They should be taught a physics course. Of course, this kind of flexibility may not exist in your institute. You should be taught a course in which they'll taught how to think like a physicist. In other words, how to use the thinking processes of a physicist rather than
Sorry for interruption, but Bikram Phookun will join us very soon. Yes, sir. Some internet connectivity is, I
Am I
think.
back?
Yeah, you are back now.
Okay, so what I was trying to get at is, if you have a physics course, let me finish here. Let me not say anything more. If you have a physics course, the basic the basic thing to learn is not how to find the motion of a ball. Okay, basic idea is how to learn how to think like a physicist. Okay, and this is a very important thing because it can help you irrespective of what you want to do. Let me stop here. Take your questions. It's 12:47, as I've spoken for 42 minutes with breaks.
Very nice, sir. Very nice.
Let me stop here and take your questions. If you have
Sir, thank you, sir. Thank you for this very important talk. And it's really. Hello. I think Dr. Phookun will join us very soon. Some internet. Okay. Okay.
Maybe you should
Am I
type out
audible,
your
sir?
questions. I can't hear.
Okay, sir.
Yeah.
Sir, you can see some questions are there, but I will recite the questions for you. Okay. There is a one questions which is posted here from Priyanka Nautiyal. She said that in recent years there is a decline interest in physics among students. So, sir, what is your perspective to this as a teacher? Am I audible?
I can't hear you.
Okay, sir. Hello. Am I audible, sir?
Can you type it out?
So you can see the questions in chat box. You can
Your
see
voice
the
is breaking. I can't hear you.
Okay, 1 minute, sir.
I can't hear you, Ashish.
Now I'm audible, sir.
Yeah, you're audible.
Now I'm audible. Okay, now. So I have just switched off my cam. Okay. One
I can
question
switch
is,
off
sir,
my camera as well if you wish.
yeah. You can also switch off your camera for better connectivity, sir.
Okay.
Okay. There is one questions posted by the Priyanka Nautiyal. Okay, so she said that in recent years there is a decline interest in physics among students. So, sir, what is your perspective to this as a teacher?
Well, I don't necessarily think that we need very large numbers of students going into physics. I don't think that will necessarily improve things. But I think what is more necessary is that some of the central lessons of physics should permeate all of science. Okay, that would be more useful than making more people do physics. Because like I said, physics is not really everybody's cup of tea. And that's perfectly okay. I think that's perfectly acceptable. But it would be nice if some of the basic ideas of physics were picked up by the other sciences and absorbed into them.
Okay, sir. Sir, one question is there from the Kulika Singh. She writes that, can we relate astrophysics to astrology?
To the best of my knowledge, no. Okay, astrology is not a science, whereas astronomy is. So astronomy and astrophysics is a science based on physics, whereas astrology is based on divination. Okay, which is more like a little bit like mumbo jumbo. So I mean, so astrology has really nothing to do with astronomy and astrophysics, except that it uses what appears to be scientific data to make predictions. So, for example, let me give you a very simple example. Okay, if I throw a ball into the air, it follows a particular trajectory. Okay, and prediction of that trajectory is part of physics. But if I throw a ball into the air and say that if the ball lands between these two trees, then you will win 1 crore of rupees in Kaun Banega Crorepati, that is not physics anymore. Even though I have used something that started as physics, I'm making a prediction that has nothing to do with physics. So in astrology, what happens is they use the motions of the planets to make predictions about things that have nothing to do with the motions of the planets. Go ahead, please. That's it. Yeah.
One of the questions from our students. Sir, what according to you is more important in physics? Is it the hypothesis or the observations? Or is it a combination of both?
It's the combination. It's a very, very good question. Okay, it's both. If you just make hypotheses without making observations, then you're a philosopher. If you just make observations without making hypotheses, then you're not really understanding your observations. You're just simply multiplying your observations. So it's the appropriate combination of the two that is physics.
Okay. Thank you, sir. Thank you. Now, sir, I think we are in the conclusive phase. So before putting my own question, it's my own question as a juvenile teacher in this field. Okay. So we have a postgraduate department in our college, and this college is affiliated to Gadwal Central University. Okay. And we are offering various courses in the life sciences, and most of the courses of life sciences they have biophysics. So our faculty, the faculty of the Department of Physics used to teach there by respective courses in the life sciences. Okay, sir. One thing is that we are also conducted in every year we are conducting an outreach program for our department. When the theme is learning through the sharing of knowledge. So we used to organize 1 or 2 day workshop in the foothills of the Himalaya, because we are located in the Dehradun, in the foothills of the Himalaya. So we go into the deep of the interior, and then we can conduct the workshop, and the workshop is conducted to our students. Okay. One thing I'm very keen to know about this. When even it's also case with me when I was in a school in 9th standard. That time we used to learn about the quantum numbers, but that time our hypothesis not matured as after post graduation, after PhD, and when we are in this teaching profession. But how we can visualize that particular hypothesis among the students, that then they can realize or understand the quantum numbers, such like a complex other topics in physics or chemistry. Can you give us some insight on this?
Well, that's a tough one. That's a very, very tough one, because essentially you've got to bring in the wave nature of particles.
Yeah.
And this is something that would be very difficult for the common person to understand, because I mean, they see a particle as a particle, they see a ball as a ball, they don't see it as a wave. Okay. So I can't think of any easy way to get the idea of quantum numbers across, because I just taught quantum mechanics this semester and the last semester. And even when you teach it with all the paraphernalia, people find it very, very difficult to understand that. So frankly, I don't know how to get it across to a common man. It's not something. It is extremely subtle. It is very, very non-obvious why particles make it.
Yeah, but most of the time we encounter this situation when we interact with the school students, because at the time they are in a just 9th or high school standards, and they are not enough mature to visualize all these concepts. But they have a lot of the things in the syllabus, just like a quantum numbers, just like for others. Even the new curriculum of the boards, they have a lot of such type of tough stuffs in their curriculum. So how as a teacher we can address them?
Let me put it this way. This is not something that I would be willing to explain in 5 minutes or 10 minutes If someone asked me what a quantum number was, I would say, look, to understand this, see, there are different things. So for example, let me give you another extreme example. They've also heard of black holes.
Yeah.
Suppose they ask you what a black hole is. You cannot provide any kind of answer to that question. So what you can do is motivate them to understand physics enough to get to the point where they will understand what a quantum number is and what a black hole is. So I don't think one should assume that it is one's responsibility to explain anything in physics, however deep, within 5 minutes, because that's simply not possible. If it was possible to do all of that, then why do we need to learn so many years of physics? The point I try to make to my students is it is not possible to understand quantum mechanics in 5 minutes. It's not possible to understand cosmology in 5 minutes. Okay, it's a process. So they've been introduced to this concept. If they're sufficiently interested, then let them come to college, and I could give them some kind of beginning of an explanation using the wave nature of particles and so on. But it's not going to get very far. And unfortunately, they have to be, well, unfortunately or fortunately, I think it's in some sense fortunate, because they have to understand that to get to the point where they will truly understand what a quantum number is, they need to put in several years of work. It's not something trivial. Okay, it's something very, very deep.
Thank you, sir. Now I think you can put on your camera so we can conclude. Okay. Thank you, sir. It's a very nice talk given by you, and especially I was very interested to listen you from your side. And thank you very much for sparing your time, valuable time with us. And definitely one thing I would like to mention in this, because as we are very juvenile in this field of teaching, and you are in this connection, your address is very valuable, and definitely we this your lecture enhance our imaginations to how to teach the physics. As you said, that notice the nature is very, very important part of teaching. So definitely we will incorporate all those suggestions which we have received from your side, and then we can little shift. We can make a little shift in our teaching styles also. So I think I would like to thank all the audience, all the students which participate in this very important programs. And finally, I would like to big thanks to Professor Bikram Phookun, because when just I message, I would like to mention one thing. I would like to share one thing to audience. When I just read about the article which published by the Professor Bikram in social media, and I used that social media connectivity is very good. And then I just messaged him, can he spare some time with us? Immediately he responded, yes, I can do it. So it shows the commitment and the instant connectivity, and it's his strong commitment towards the science. So it's a very biggest thing, and we all inspire from his work. And he's in a very prestigious college of this country, and definitely he's a very good thinker, and he's an inspiration of lot of the young teachers and researchers in this country. Thank you, sir, for your valuable time, and good day to all.
All right. Thank you very much. Bye.
Thank you, sir.
Okay. Bye.